In the beginning, there was nothing. Well, that's not entirely true. In the beginning, there was everything. It was hot, dense, infinitely small, and it was in a state of perfect balance. Then something happened. Space expanded, time began, and the universe was born. That moment is known as the Big Bang. And while we think of the Big Bang as an explosion, it wasn't an explosion in space. It was the expansion of space itself. In other words, space became bigger. And because everything was contained within that space, everything got bigger too. This is still a bit of a mystery to scientists. It's like asking what's outside of a circle. If you go around the edge, you always find more circle. Well, in the same way, if you go back in time before the Big Bang, you would still find more Big Bang. There was no outside of it, no beginning before it. And so the idea of something causing the Big Bang doesn't really apply. But that's a topic for another video. For now, let's just take the Big Bang as a given. Let's assume that our universe started out as a hot, dense, infinitely small point, and let's see what happens next. Less than a second after the Big Bang, the universe was still incredibly hot and dense. The average temperature was about 10 billion degrees Celsius. At this stage, the fundamental forces that govern the behavior of matter had not yet separated. Gravity, electromagnetism, and the strong and weak nuclear forces were all one. As the universe continued to expand, these forces would separate, and the universe as we know it would begin to take shape. But in that first second, they were all one. At this extreme temperature, the very concept of a particle had not yet formed. There was no such thing as an empty vacuum either. Even the vacuum was seething with energy. But as the universe expanded and cooled, things began to change. At around 10 million trillionths of a second, the first particles appeared. The simplest type of particle is the one we are most familiar with, the photon. Photons are elementary particles, meaning they are not made up of anything else. They are the quantum of electromagnetic energy, the smallest possible packet of light. But photons don't have mass. And in the early universe, the photons bouncing around were moving so fast that they were almost impossible to detect. So we won't worry about them for now. Instead, let's look at the other simple particles, the building blocks of matter, protons, neutrons, and electrons. These particles do have mass. Protons and neutrons can combine to form atomic nuclei. Electrons will orbit those nuclei, but only after the universe has cooled down significantly.
No.
That doesn't happen until around 100 millionths of a second after the Big Bang. But during that first second, these particles are still zipping around in a chaotic sea of energy. Because their motion is random, their average speed is related to the temperature of the universe. The hotter the universe, the faster these particles move. But there is one key difference between the particles. Protons and neutrons are neutral, meaning they carry no electric charge. Electrons are negatively charged. That tiny detail has enormous consequences. As the universe expands and cools, protons and neutrons can combine to form atomic nuclei. Now, here's the problem. Normally, like charges repel each other. But in the early universe, these particles are moving so fast that sometimes two protons will collide with enough force to overcome their mutual repulsion and stick together. If this happens, the excess energy is released as radiation. The same is true for neutrons. But if a proton and a neutron collide, the excess energy is carried away by a photon. This process is called the inverse photoelectric effect. It is important because it allows protons and neutrons to overcome their mutual repulsion and form the nuclei of elements like hydrogen and helium. Electrons, on the other hand, can't participate in this process. Their negative charge prevents them from combining with each other. But once the universe has cooled enough for them to slow down, they can form chemical bonds with protons and nuclei. And that's when the first atoms are born. We've come to the end of the first second. During this time, the universe has gone from an infinitely small point to a vast expanse of space. Elementary particles have been created, atomic nuclei have formed, and the stage is set for the formation of the first atoms. But the real fireworks are still to come. Over the next few minutes, the universe will continue to cool, allowing electrons to settle into their lowest energy state. That will trigger the formation of the first hydrogen atoms. And with that, the era of the simplest element will dawn. What happens next is anyone's guess. Stars will form, galaxies will coalesce, and cosmic structures will emerge over billions of years. But it all starts with that first second, the cradle of creation. It's hard to overstate the significance of this moment in human history. It represents our first glimpse into the fundamental nature of reality. For millennia, humans have pondered the origins of the universe. But it was until relatively recently that we began to understand the physical processes that govern the cosmos. The birth of stars and galaxies, the composition of planets, the structure of atoms, it all traces back to this moment. By understanding the first second, we understand the universe itself. In the next episode, we'll explore what happened after that first second. How did the universe evolve from a hot, dense state into the vast expanse we see today? What forces shaped the early cosmos, and what role did matter play in that process? Join us as we continue our journey through time to uncover the secrets of the early universe. Don't forget to subscribe and leave your comments below. See you soon. As you'll hear me say many times throughout this series, protons and neutrons, those positively charged particles found in the nucleus of atoms, were not around for most of the history of the early universe. You can check out my earlier video called What Are Those? For more details, but here's the quick version. Protons and neutrons are composite particles, each made up of 3 quarks held together by gluons. The carriers of the strong nuclear force, the conditions of the early universe were such that the quarks just could assemble into protons and neutrons. It was until the universe had cooled down to around YD degrees Celsius that these particles started to form. That may sound ridiculously hot, but it's really cold compared to the unimaginable temperatures of the moments immediately following the Big Bang. After around 10 to 6 seconds, the universe had cooled enough for protons and neutrons to combine to make atomic nuclei. Nuclei, the stuff inside atoms, which is what makes them different from just positively charged bare protons. Most of these nuclei were helium, since they only require 2 protons and 2 neutrons to form. A few hydrogen nuclei, though, managed to exist, each consisting of just a single proton, with some of the neutrons floating around waiting to be captured by the remaining protons. The universe was no longer a sea of free protons and electrons. It was a mix of atomic nuclei and electrons whizzing around at half the speed of light. This was the era known as the photon epoch, or the era of photon domination, lasting from around Y-6 seconds to around 380,000 years after the Big Bang. The universe was opaque in the extreme. Free electrons, scattered photons, meaning that light couldn't travel far before being absorbed and re-emitted in a random direction. However, as the universe expanded, the electrons eventually dropped their energy levels low enough to start combining with nuclei to make atoms. Once bound into atoms, the electrons could no longer scatter photons, and the universe became transparent. The light, which had been so jumbled during the photon epoch, could finally stream across the cosmos unhindered. We can see this light today in the famous cosmic microwave background, a faint glow that bathes the entire sky and carries within it the imprints of the hot plasma from which stars and galaxies later formed. With the universe now transparent, there was nothing preventing the neutral hydrogen atoms from drifting together and forming molecular hydrogen. Gravity tugged the atoms together, compressing them into cool, dense clouds. Gravity also pulled these clouds together. In turn, triggered a runaway fusion reaction in which the cores of the hydrogen atoms were forced together at tremendous pressures, and temperatures high enough to overcome the electrostatic repulsion between the protons and fuse them into helium. Stars were born, and along with them gigantic dust clouds, cocooning off molecular hydrogen for future generations of stars. With the formation of the first luminous objects, the universe had entered the era of the stars. But let's go back to the photon epoch, because there's something strange going on. If you want to learn more about general relativity, you probably think you need to study curved spaces and differential equations. And you wouldn't be wrong. But if you're looking for a way to develop your intuition about curved spaces, then you should definitely check out today's sponsor, Brilliant Who's course on general relativity. It can help you develop your intuition for curved spaces. In the first minutes following the Big Bang, the universe was incredibly hot. Temperatures reached unimaginably high levels, much hotter than anything we can reproduce on Earth. This meant that every particle in the universe was zooming around at relativistic speeds close to the speed of light. Since energy and mass are interchangeable, the photons streaming around the universe had a tremendous amount of mass. Remember Einstein's equation E equals mc squared, where E represents energy and mc squared represents mass? When we move things, we increase their kinetic energy. However, when we move things close to the speed of light, that kinetic energy quickly converts into mass. Thus, the kinetic energy of the universe's photons contributed significantly to the total mass of the universe. And here's the weird thing. This energy contributed to the gravitational field of the universe, meaning that all of the photons in the universe attracted one another gravitationally. The effect was extremely subtle, but it did exist. It was until the universe had cooled and the photons had slowed down that we stopped noticing this gravitational attraction between photons. We typically do unnotice this attraction under normal circumstances, simply because the rest of mass is so much more significant than the mass associated with light. However, in the moments following the Big Bang, it was the only noticeable gravitational pull in the universe. That's right, gravity played no role whatsoever. In the behavior of matter in the first minutes after the Big Bang, only the photons attracted one another. The other forces of nature, the electromagnetic force and the strong and weak nuclear forces, were the only forces shaping the interaction between matter. It took over 300,000 years for the universe to cool sufficiently for the atoms to stop moving quickly enough to notice this gravitational interaction between photons. But once the universe had cooled enough to allow atoms to form, gravity was suddenly everywhere. As the hydrogen atoms combined into helium, it's thought that the excess energy released left the atoms in excited states. These excited states are analogous to the orbits in the Bohr model of the atom. You may remember from your high school physics class that these orbits are quantized. The electron can't be halfway between orbits. It must drop from one quantized level to another. In the same way, the atoms in the early universe were stuck between quantized energy levels. They were unable to drop to lower energy levels and release visible light. It was until the universe had expanded and cooled enough for the atoms to fall to their lowest energy levels that the universe was flooded with light. Light which we can still see today in the cosmic microwave background, around 1 billion years after the formation of the first stars. The universe had cooled to the point that the electrons and atoms could no longer be knocked free by ultraviolet light. Instead, the atoms absorbed only lower energy light, mostly in the infrared. Visible light bounced off of these atoms without being absorbed. This is why the first galaxies are thought to have been opaque to visible light. It wasn't until the universe had expanded again, allowing the atoms to cool further, that the universe became transparent to visible light. The first galaxies would have glowed like neon signs, emitting ultraviolet and infrared light as their atoms fell to their lowest energy levels. But since they were opaque, we can't see them. For a long time, astronomers believed that the first galaxies would be the brightest objects in the early universe, but they've turned out to be disappointingly dim. That's because these objects were almost entirely composed of hydrogen, which has only one electron per atom. Thus, there aren't many ways for these atoms to absorb light. They were like a pane of glass, except for a couple of helium atoms that were opaque to ultraviolet light. The majority of the light came from much heavier elements that astronomers didn't expect to find in the early universe. These are the population 3 stars, huge masses of helium and other metals like carbon, oxygen, and iron. Where did they come from? The answer seems to lie in the period known as Big Bang nucleosynthesis, occurring from about 1 minute to 20 minutes after the Big Bang. The universe was still hot enough for protons and neutrons to combine into atomic nuclei. But the abundance of neutrons was dwindling due to the radioactive decay of neutrons into protons. Thus, the window for nucleosynthesis was short. During this time, the universe was a maelstrom of activity as protons and neutrons smashed into one another, fusing into increasingly heavier nuclei. Some of these nuclei were isotopes of existing elements, such as deuterium, which has 1 neutron and 1 proton, and helium, which has 2 neutrons and 2 protons. Others were extinct today, such as tritium, which has 2 neutrons and 1 proton, and helium-3, which has 1 neutron and 1 proton. By studying the observed abundance of light elements in the universe today, scientists have been able to work backwards, inferring the conditions that existed in the early universe. They discovered that there had to have been a lot of neutrons for nuclear fusion to produce these large quantities of lithium and helium. But where did they all come from? There are 2 possibilities. Either the neutron was created during the initial moments of the Big Bang, or it was created by a particle called a neutron. These sterile neutrinos are hypothetical particles that were proposed in the 1970s. However, attempts to detect them have failed and they remain purely hypothetical. While most of the helium in the early universe consisted of helium-4, the abundant isotope we know today, a small amount was helium-3. Some of this helium-3 was destroyed when it captured an electron and turned into lithium. The rest, however, survived until the formation of stars, where it was incorporated into the atmospheres of Jupiter-like planets and became part of their makeup. Today it's thought that most of the helium-3 in the universe is trapped inside the gas giants of the Milky Way. One day, perhaps we'll be mining it to power the human race. So what's next? Well, it's difficult to say. The transition from a quark-dominated universe to one dominated by atoms took hundreds of thousands of years. But the transition from a hydrogen-dominated universe to one dominated by helium will take billions of years. If the first galaxies were powered by population 3 stars, massive balls of helium burning furiously before collapsing into neutron stars or black holes, then we might find ourselves entering an era of helium domination. But it could be trillions of years from now. I hope you enjoyed this video. If you did, please subscribe to my channel and check out my latest video on the weird reality of wormholes. Thanks for watching. What existed before the Big Bang? I know it sounds like a question with an unanswerable answer, but let's think about it. If you go back in time, we know from Einstein's theory of general relativity that the universe can only be so infinitely small and infinitely dense, a singularity. But we also know that something happened at that moment. Something triggered the expansion of the universe, the Big Bang. So what was it? What was around and what happened at that moment? Here's what scientists think. You have to go back to when the universe was a fraction of a second old, just 10 to the negative 43 seconds, or a quarter of a trillionth of a second. At this moment, the fundamental building blocks of matter roamed freely. Quarks are the constituents of protons and neutrons, but at these temperatures, trillions of degrees, they could not yet bind together. Instead, they formed a quark-gluon plasma, a soup so dense and hot that it behaved like a fluid. It was a weird state of matter, almost like nothing we know. There was so much energy around that the normal rules of physics didn't apply. Forces were so strong that they ripped apart any attempt at creating stable matter. All we know is that at some point the temperature started to drop. As the universe expanded and cooled, things started to change. First, the quarks began to bind together to form composite particles called mesons, which are made up of a quark and an antiquark. Then other mesons came along and started smashing into those pairs, making for quarks. And then finally, at a temperature of around 2 trillion degrees, enough energy was released to allow quarks to form stable groups of 3. These groups of 3 quarks became the first protons and neutrons. This transition is called hadronization because it's when these particles known as hadrons first appear. After that, the universe was a little less chaotic. Protons and neutrons could now exist, setting the stage for the eventual creation of atomic nuclei. At the end of the first second, the universe was a rapidly expanding sea of protons, neutrons, electrons, neutrinos, and photons. The temperature was about 10 billion degrees Kelvin, still unimaginably hot. Space was still filled with intense radiation, and matter and energy were still locked in a fierce struggle. But the stage was set for the cosmic drama to unfold over billions of years. Think of it like this. The first second of the universe was like a cosmic game with the rules set for everything that came after. The very first second determined the constants of nature, the relative abundance of particles, and the seeds of cosmic structure. Without that initial condition, we wouldn't be here.
No.
Everything we see around us, every galaxy, every star, every planet, every living being is a consequence of what happened in that brief window. But why did the universe start out in such a strange way? Why were there almost no atoms? Why was it mostly empty space? The honest answer is we don't know, but this much we can say with confidence. Our universe is very unusual. Most universes, if not all, would have been very different. That S, because the conditions that led to the formation of our universe are extremely unlikely to occur by chance. For example, the values of the fundamental constants of nature, such as the strength of gravity or the mass of the electron, are finely tuned so that stars like our sun can form and life can evolve. It's almost as if the universe had a purpose. In our quest to understand the origins of the universe, we often focus on the Big Bang and the moments immediately preceding it. But the story doesn't end there. The events of the first few minutes were equally crucial in shaping the cosmos we know. From the fiery birth of elementary particles to the formation of the lightest elements, each step was a building block in the grand scheme of cosmic evolution. Our universe, just 1 second old, was unimaginably different from today. Yet hidden in that fiery infancy were all the ingredients of the cosmos we know. The first second was not just the beginning, it was the foundation. It was the cosmic game with all the rules written in the first moments. It's a testament to the elegance and precision of the laws of nature that even in the wildest chaos, order emerges, giving rise to the stunning complexity of the universe we call home. So what do you think? Does the idea that the universe was once a quark glue and plasma, a primordial soup of elementary particles, both fascinate and terrify you? Let me know your thoughts in the comments below. We are living in an amazing era. Thanks for watching. See you next time. 1 second after the Big Bang, the universe was transformed from a sea of fundamental particles to a dynamic mix of atomic nuclei. Protons and neutrons were engaged in a cosmic balancing act, setting the stage for the creation of elements like hydrogen and helium. We've left the realm of particle physics and entered a world of atomic beginnings. And as the curtain rises on Act 2, the elements are set. Now the show must go on. Let us explore what happened after that pivotal first second and how the cosmic choreography continued to shape our universe. Join me on a journey back to the dawn of time to witness the birth of the first stars, the emergence of galaxies, and the echoes of the Big Bang that still resonate today. It's a great equalizer. A second in the life of the early universe at the start of our story. Just 1 second after the Big Bang, the universe was an inferno of fundamental particles. Protons and neutrons swam in a sea of unimaginable energy. There was no space as we know it, no atoms, no light, not even a hint of the complexity that would unfold. Everything was in flux, governed by the laws of quantum mechanics and the relentless march of cosmic evolution. But within this fleeting second, the foundations of our material world were laid. The delicate balance between protons and neutrons was key. If there were too many or too few neutrons, the subsequent creation of elements would be altered, potentially changing the very fabric of our existence. From a human perspective, a second is a blink of an eye, but cosmologically it was an eternity. It bridged the gap between the tiniest subatomic particles and the first steps towards the formation of elements, atoms, and eventually stars. It's a testament to the power of time and the elegant simplicity of the laws that govern our universe. As we leave the first second behind, we enter an epoch where matter and energy continue their complex dance. 1 second may seem trivial in human terms, but cosmologically it was monumental. That brief span determined how the universe would evolve for billions of years. But to fully understand what followed, we need to trace the next milestones. The iconic events and objects that rose out of that primordial plasma, shaping the universe into something recognizable. The birth of light nuclei, hydrogen and helium entered the stage. As the universe expanded and cooled, the high-energy state of the protons and neutrons began to shift. Around 1 second after the Big Bang, temperatures had dropped to about 10 billion Kelvin. This marked the beginning of an era known as Big Bang nucleosynthesis, or BBN. This period lasted until about 3 minutes after the Big Bang, when the universe had cooled sufficiently for atomic nuclei to form. During BBN, the protons and neutrons started to come together in a delicate ballet, creating the first light nuclei. The most common of these was, of course, hydrogen, formed when a single proton captured an electron. But some protons managed to capture 2 neutrons to form deuterium, which in turn could capture another proton to create helium. Trace amounts of lithium and tritium were also produced, although these were much rarer. This wasn't just a random process. It was a carefully balanced act, driven by the laws of nuclear physics. The exact proportions of these elements were determined by the balance between the number of protons and neutrons, the temperature, and the rate of expansion of the universe. At the end of this epoch, the universe was mostly hydrogen and helium, with tiny traces of other elements. The significance of this can't be overstated. This simple mixture became the building block of cosmic evolution. Stars, galaxies, and planets would coalesce from this primordial broth, and the elements forged in the hearts of stars, would enrich the universe with even heavier nuclei. First stars, first galaxies, a new era dawns after BBN. The universe continued to expand and cool. The stage was now set for the next great act in the cosmic drama, the first stars and galaxies. For hundreds of thousands of years, the cosmos was a hot, opaque plasma. Light could not travel far before being absorbed or scattered by free electrons. But as the universe cooled further, electrons combined with nuclei to form neutral atoms, releasing a surge of photons. This event, known as recombination, made the universe transparent. Photons could now travel unimpeded, stretching into the microwave part of the spectrum. This microwave background radiation is still detectable today and provides a snapshot of the universe as it was. 380,000 years after the Big Bang, it's a testament to the power of observation that we can peer so far back in time and witness this pivotal moment in cosmic history. But transparency brought new challenges. The absence of light meant that the universe was plunged into darkness. It's a strange concept to us now, given that darkness is something we experience every day. But for the early universe, it was a defining feature of its epoch, known as the Cosmic Dark Ages. Matter clumped together under gravity, forming dense regions that would become the seeds of galaxies. Stars ignited, bringing light and heat back into the universe. This marked the end of the Dark Ages and the beginning of a new era of cosmic enlightenment, the dawn of structure. Seeds of galaxies and clusters, as the first stars ignited, they began to sculpt the very fabric of the universe. Their light, heat, and stellar winds blew away the fog of gas, creating bubbles of emptiness in which new stars could form. These stellar nurseries gave birth to the first galaxies, vast islands of stars held together by gravity. Gravity continued to weave its magic, pulling galaxies together into clusters and superclusters. These colossal gatherings of galaxies became the stage for even grander cosmic events. But the interplay of gravity and the distribution of matter didn't stop at galaxies. It extended to the largest structures in the observable universe, the cosmic filaments and voids. These immense formations stretch across billions of light years and contain thousands of galaxies each. They are the grand tapestry of the cosmos, woven together over billions of years by the invisible hand of gravity. Cosmic evolution. Echoes of the past and the present as we survey the universe today. We are witnessing the culmination of billions of years of cosmic evolution. From the simplest atoms to the grand tapestry of galaxies, everything we see is the product of a long and intricate history. And throughout this journey, the echoes of the past resonate in the present. For instance, the cosmic microwave background radiation, a mere 380,000 years old, holds within it the imprints of the first stars and galaxies. These faint signals provide an invaluable window into the early universe. Similarly, the abundance of elements like helium and lithium reflects the outcome of Big Bang nucleosynthesis. The very fact that we can exist, that we are made of star stuff, is a testament to the delicate balance of processes that unfolded in the first few minutes after the Big Bang. Moreover, the distribution of matter in the universe. The way galaxies and clusters are grouped and separated bears the signature of the initial conditions set in the first second. Those tiny fluctuations in density, smaller than a quantum of light, became the seeds of the cosmic structures we see today. Understanding these echoes is crucial. It allows us to reconstruct the cosmic timeline, to piece together the history of our universe from the smallest atoms to the grandest galaxies. It's a cosmic detective story, where every observation is a clue leading us closer to the heart of the Big Bang. The unknowns in the quest for understanding, while we've come a long way in unraveling the secrets of the first second after the Big Bang, there are still unknowns. The exact nature of the particles that existed in this extreme environment, their interactions, and the conditions under which they formed, all remain subjects of intense research. Scientists are working to recreate these conditions in particle accelerators, searching for answers in the most fundamental building blocks of matter. Moreover, understanding the transition from a quantum field to a classical universe, how order arose from apparent chaos, is a profound mystery. It touches on the very foundations of physics and cosmology, and could revolutionize our understanding of the universe. In the quest for knowledge, there will always be more questions than answers. But the journey of discovery is just as important as the destination. Each new finding, each piece of the puzzle, deepens our appreciation for the complexity and elegance of the laws that govern our existence. The first second after the Big Bang was a moment of immense power, a moment that set in motion the events that led to the birth of stars, galaxies, and ultimately life itself. It was a moment that transformed a sea of fundamental particles into the rich tapestry of the cosmos we see today. And as we continue to probe the depths of the universe, seeking to understand our place within it, we are reminded of the profound truth. We are truly children of the cosmos, born from the same elements that formed the first stars, nurtured by the light of the same sun that bathes our world in warmth and guides our journey through life. We are connected to the universe in ways we are only beginning to understand. And as we look up at the night sky, we are gazing back at ourselves, at the very origins of our being. This channel presents a moment in time. 1 second after the Big Bang, the universe is already changing. At this early stage, protons and neutrons are combining to form atomic nuclei. They're capturing free electrons to make atoms, and those atoms are glowing a brilliant crimson. But all these processes are happening over a backdrop of seething plasma and radiation. It's a harsh environment. So what does this period of rapid change tell us about how the universe began and what comes next? That's what we'll find out in today's video. It's me, and this is the channel. We've talked about the first few minutes of the universe before. Just look at this video. But today, let's go back even further. Let us try to get to the bottom of what happened during the very first second after the Big Bang. The moment when fundamental forces split and the universe turned from a featureless expanse into a bubbling cauldron of elementary particles. The first second is really 3 moments in one, each separated by thousands of years. There's the instant after the Big Bang itself, the moment of nuclei synthesis, when protons and neutrons combine to form the simplest atomic cores. Then there's the epoch of recombination, when the universe cools enough for electrons to be captured and full-fledged atoms form. Finally, there's the era of decoupling, when photons finally become free to roam the universe. Let's start at the beginning. The first fraction of a second is dominated by fundamental forces. The 4 forces of nature we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. They're all joined together in a single superforce at unimaginable energies. As the universe rapidly expands and cools, that superforce breaks down into the electromagnetic force and the 3 forces of the Standard Model: the strong force, the weak force, and gravity. Quarks come together under the strong force to form the nuclei of protons and neutrons. Those nuclei then capture free electrons to form the first atoms. It's mostly hydrogen, but also some deuterium, which has 1 proton and 1 neutron in its nucleus. All this happens within a microsecond. The key takeaway is that this is a sea of nuclei and electrons, almost like a gigantic plasma. Photons bounce off free electrons, unable to penetrate further. The universe is opaque. After a few minutes, things begin to cool a little. Protons and neutrons can no longer sustain each other, and the nuclei begin to bind up electrons. The universe becomes transparent. Photons stream outward, carrying energy from the hot plasma. That's the observable universe today, the cosmic microwave background. For 380,000 years, the universe is quiet. There's almost no activity on the grand scale, no galaxies, no stars. Space is still very empty, but something big is brewing. Atomic hydrogen, the most abundant element, begins to clump together in enormous gas clouds. Within these clouds, a new process starts. Gravity pulls electrons away from hydrogen nuclei, turning the gas into a plasma once again. These clouds are so massive that electrons don't have anywhere to hide. They're trapped. The universe is once again opaque. This is the second major transition of the period, the end of the Dark Ages and the beginning of the cosmic dawn. Let's talk about the third and final phase. During the first million years, the universe is too hot for chemical activity. Only the most basic elements, hydrogen, helium, and lithium, are created inside the hot core of stars. But as the universe continues to expand and cool, the first stars will trigger a chemical revolution. When those stars explode, they scatter carbon, oxygen, and iron into space. These are the ingredients of rocky planets, oceans, and ultimately life. These three moments, nucleosynthesis, recombination, and decoupling, represent the birth of the universe as we know it. They represent the transition from physics to chemistry. So to summarize, here's what happened during the first second. At 0 seconds, we have a hot, dense, featureless plasma. No forces have separated, no nuclei have formed. At 1 second, we have a universe of simple nuclei and electrons. Nothing has recombined into atoms yet. At 380,000 years, we have a universe of simple atoms and photons. Hydrogen has recombined. Photons are streaming through space. At 1 million years, we have a universe of more complex elements and stars. Carbon, oxygen, and iron have formed. Stars are scattering heavier elements into space. So this was a pivotal era. The seeds of everything that came later were planted during this brief opening chapter. And it wasn't just what happened, it was what didn't happen. No galaxies, no planets, no stars, no chemical activity. But all this would soon change. The first stars exploded. The first galaxies formed. The first planetary systems assembled. It's hard to overstate the importance of this era, but if we want to understand what actually happened, we need to keep looking for evidence. There are two main ways astronomers do this. The first is by analyzing the cosmic microwave background, or CMB. The CMB is a snapshot of the universe. 380,000 years after the Big Bang, it reveals a universe that's very homogeneous and isotropic, meaning it looks the same in every direction. Tiny variations in the CMB's temperature reveal where matter was slightly more dense. Those denser regions eventually became the galaxies we see today. The second method is studying the intergalactic medium, the tenuous gas between galaxies. This gas contains large quantities of helium and some of the heavier elements produced by the first stars. Astronomers are also searching for the faint glow of the epoch of reionization. When the universe was filled with plasma again, light could no longer travel freely through space. This glow may reveal the distribution of the first luminous objects, but it has yet to be detected. So the story of the first second is far from over. These events forever shaped the evolution of the universe. Without nucleosynthesis, there would be no hydrogen to form stars. Without recombination, there would be no light to study. Without the first stars, there would be no carbon, oxygen, or iron, the building blocks of life. The first second may have laid the foundation, but these cosmic milestones gave the universe form, color, and potential. They represent the steps from pure physics to the beginnings of chemistry, from chaos to order, from darkness to light. Each moment was a turning point. So if you think the history of the universe is fascinating, wait till we get to this era. In this video, I'm going to cover the formation of the first galaxies and supermassive black holes. It's another pivotal period in cosmic history. You won't want to miss it. But before we go, I want to hear from you. What did you find most surprising about the first second? Is there anything we should have included that we didn't? Leave your thoughts in the comments below and follow for more updates. In the beginning, there was a lot of heat, an unimaginable inferno that has never been matched since. There were also fundamental forces that would go on to shape everyday reality, but they weren't working together yet. They were separate, fractured players waiting for their moment on the field. As the universe expanded and cooled, those forces fused, shaping the fundamental particles of nature and their interactions, establishing the basic rules of reality. And just like that, the stage was set for the universe as we know it. That's what we think happened anyway. When you zoom out to view the entire universe, it looks pretty uniform, featureless, bland. Look around you and you see stuff. Stars, planets, clouds, cats, and you ask yourself, how did we get from there to here? Well, it turns out that journey is a lot more complicated than you might imagine. In this first episode of Cosmos, a space-time odyssey, we've traced the first second of the universe and followed it through its earliest milestones: nucleosynthesis, recombination, the first stars, and the birth of galaxies. Those stages are well supported by theory and observation. But when we look deeper, when we try to unravel why these things happened the way they did, we encounter some of the most profound mysteries in modern science. In this segment, we'll step beyond the established narrative and into the frontier of cosmology, where scientists are still grappling with unanswered questions. These puzzles aren't minor details. They're fundamental to understanding the universe itself. We don't know much about the conditions in the first second after the Big Bang, because there wasn't much stuff around to interact with light. Photons were bouncing off protons and neutrons in an opaque sea called a plasma, and that really hot plasma. No light could travel far before getting absorbed and re-emitted in a random direction. So the universe was a blurry, featureless place. But then something amazing happened. As the plasma cooled, the protons and electrons came together to form neutral hydrogen atoms. Voila! Suddenly, light could zip through space almost unimpeded, revealing a previously unseen universe. This process is called recombination. It unleashed the photon that would eventually carry our light into space and across the vastness of the cosmos. Before that, though, those photons had to find their way out of a tangled mess of matter. The universe was filled with gigantic, uneven clumps of matter and plasma, and photons struggled to escape their grasp. It was like fog in a crowded, dark city. As the fog gradually cleared, the universe became transparent. All of a sudden, we could see across the cosmos, at least in theory. Scientists believed the universe was actually transparent long before light could move freely. That's because the matter in those early clumps was mostly hydrogen, the simplest element in the universe. But once the clumps got a little bigger, things changed dramatically. Gravity dragged in heavier elements, forged in the cores of long-dead stars. Heavier elements tend to clump together into larger bodies, so in the densest regions, iron and nickel fell toward the core, creating a heavy knot in the center of otherwise diffuse clouds of hydrogen. Those knots grew over billions of years into the first stars, the seeds of galaxies, and the universe was never quite the same again. But what caused those knots to form? We don't know exactly. What we do know is that those clumps needed some sort of glue to bind them together, something heavier than hydrogen. But where did that come from? One leading theory proposes that those clumps arose from waves of matter that sloshed around in the early universe. These waves were ripples in a field called the inflaton field. The inflaton is hypothetical, a mathematical construct used to describe the behavior of the universe in the first moments after the Big Bang. At least 6 models of inflation exist, and there's no shortage of candidates for the inflaton particle. Each possibility makes testable predictions about the properties of matter in the early universe, and how it evolved into the structures we see today. So far, none of those predictions has panned out, which means we're still struggling to explain the origin of the first stars. Another question that continues to confound scientists is how those clumps of matter stayed intact. As matter condensed into those early stars, gravity started tugging at the edges. But as long as a clump of matter stayed above a certain mass, it was stable. Below that critical threshold, gravity won out, dispersing the clump. But we don't understand why some clumps escaped that fate, while others didn't. Recent research suggests that quantum effects played a role, but it's still early in this line of inquiry. Once the first stars ignited, the universe took a big step toward adulthood. These nuclear furnaces fused hydrogen into helium, enriching the cosmos with new elements and seeding future star systems with the building blocks of life. Stars also served another vital purpose. The gravity yanked matter out of the diffuse haze, pulling it together into clumps that would become the next generation of stars. Over millions of years, those clumps coalesced into giant assemblies of stars, the first galaxies. But how did they evolve into the structures we see today? Unfortunately, scientists don't know the answers, but they have a few clues. Most galaxies have flat, rotating disks, surrounded by massive bulges and halos of old stars. That pattern suggests that something imposed order on this chaotic jumble. Some researchers have suggested that those early galaxies formed from the remnants of immense gas clouds that collapsed in slow motion. Other scientists have proposed that rogue black holes kicked supermassive black holes into the hearts of galaxies, setting the stage for cosmic evolution. Many scientists favor a combination of both scenarios, but despite recent progress, there are still lots of open questions. For example, we don't know what determines the size of a galaxy's central bulge, and we don't know why some galaxies form bulges at all. As the universe continued to expand, cool, collapse, and reform, these galaxies encountered one another, colliding, merging, scattering, and regrouping. Today, galactic collisions are relatively rare, occurring once every 100 billion years or so. But in the early universe, encounters were frequent and violent. Galaxies jostled one another like bumper cars, stripping away huge swaths of stars and flinging them into intergalactic space. Scientists studying distant galaxies have actually seen a lot of this debris. It appears as a hazy cloud surrounding many galaxies in the early universe. But we do not know whether those clouds are debris from ancient collisions or raw material awaiting assembly into new stars. The good news is that scientists are making steady progress on these problems. One day soon, they may even be able to show why the universe has grown so grand, so intricate, and so beautiful. For now, we can marvel at the mystery. So there you have it, a brief overview of the first second of the universe and the challenges that still remain. From the separation of matter and antimatter to the formation of the first stars and galaxies, there's so much we've been able to discover about the origins of our cosmos. But there's also a lot we don't know, and that's okay. Unknown is where science gets exciting. Every unanswered question is a mystery to be solved, a puzzle to be unraveled. And as long as there are mysteries in the universe, there will be scientists eager to uncover them. If you enjoyed this video, make sure to stay tuned for more updates. And if you want to learn more about the fascinating world of space, check out the links below. Thanks for watching, and keep looking up. In the span of a second, the cosmos went from unimaginably small to unimaginably vast. It's hard to overstate just how dramatic this transition was. For most of human history, we assumed the universe had always been here, infinite in time and space. But in the 20th century, we realized the universe began with a bang and has been expanding ever since. Today, astronomers can see so far back in space that they actually looking back in time to the first 100 billionths of a second after the Big Bang. What they've seen is enough to revolutionize our understanding of reality. They've glimpsed the birth of matter, the emergence of the first elements, the formation of the first stars and galaxies. They've witnessed the evolution of the universe from an infinitely small point to the vast cosmos we inhabit today. Here's what we do know about the first 100 billionths of a second after the Big Bang, and what we're still trying to figure out, the birth of the web. The period known as cosmic inflation lasted less than a billionth of a second, yet it profoundly affected the universe's evolution. During this time, space expanded exponentially, stretching like a rubber sheet pulled taut between two fingers. Outward-bound light stretched into microwave radiation that fills our skies today. As the universe expanded, it cooled, allowing subatomic particles to form the building blocks of protons and neutrons. Within minutes, those combined to form the first atomic nuclei, mostly hydrogen and helium. But these elements were in a plasma state, meaning electrons were free to roam. As the universe continued to cool, those electrons combined with nuclei to form neutral atoms. The free electrons became less and less energetic, dropping to ever lower energy levels. Eventually, when the energy levels dropped low enough, the electrons combined with nuclei to form the first rudimentary atoms, mostly hydrogen and helium. This process is called recombination, and when it happened, the universe became transparent. Light could travel unimpeded for the first time. It was the end of the era of the cosmic soup. The stuff that made the first stars and galaxies was born. But how did those stars and galaxies come together? Enter dark matter. Astronomers have long noticed that the amount of gravity in the universe does unseem to match the amount of matter. There's just too much gravity, and they attribute this discrepancy to a mysterious substance called dark matter. While we can't see dark matter directly, we infer its presence through its gravitational effects. In the early universe, this dark matter would have formed a sort of scaffolding. As the universe expanded, collapsed, and then expanded again, the dark matter provided the basis for the first large-scale structures. Normal matter would have collapsed onto these structures, forming the seeds of galaxies and galaxy clusters. Accelerating expansion. At first, the expansion of the universe seemed to slow down over time, as you might expect. Gravity pulls everything inward, so it should pull the universe inward too. But in the late 1990s, astronomers discovered that the expansion of the universe is actually speeding up. Something is pushing space apart faster and faster, and we call this mysterious force dark energy. But we do know exactly what dark energy is, or whether it was around in the first second. Some cosmologists believe that dark energy is a property of space itself, a constant built into the very fabric of space-time. Others think it's something that evolves over time, yet others think it might even decay in the distant future. Understanding dark energy's role in the earliest moments would help cosmologists understand its influence today. These mysteries leave us with one final question. How can we possibly hope to understand the moment before the first second? When we try to apply our current theories of physics, they break down. Einstein's theory of general relativity says that the universe began from a state of infinite density, and quantum mechanics says it could have been smaller than the Planck length, tiniest possible length in the universe. How can infinite be the same as zero? We need a new theory of quantum gravity to resolve this paradox, a framework that merges the principles of general relativity with those of quantum mechanics. There are a lot of candidates, but none are widely accepted. Most popular ones suggest that space is actually quantized, made up of tiny loops or vibrating strings. These ideas hint at the possibility that the Big Bang was not the beginning, but a bounce from a previous universe, or that our universe is just one of many in a vast multiverse. Unfortunately, we don't have the data we need to test these ideas yet. We're still at the stage where physicists were for the theory of general relativity a century ago. Nonetheless, researchers are confident that a theory of quantum gravity will ultimately explain how space emerged from something deeper and vaster. The first second, a cosmic time machine. So what can we say about the first second? In short, we're just beginning to find out. Clues are faint, but they're there if we know where to look. With powerful telescopes and cutting-edge detectors, scientists are scouring the skies for signals from the first stars and galaxies. By analyzing the light from distant galaxies, they can reconstruct the conditions that gave rise to the first luminous objects. Meanwhile, experiments like the Square Kilometre Array in South Africa and the James Webb Space Telescope promise to peer even deeper into the early universe. As these and other projects come online, we can expect a flood of new data that will shed light on the darkest recesses of the first second. What secrets will they uncover? No one knows. But the first 100 billionths of a second after the Big Bang was a time of profound change, a cosmic instant that shaped the universe we inhabit today. By understanding it, we gain insight into the very nature of reality. In that first second, time began, and in doing so, it also established the conditions for everything that would follow, including the planet we call home and the life it harbors. And yet the universe has barely begun. Those first 100 billionths of a second represent less than 1% of the age of the universe. What happened next? Watch as the universe evolves over billions of years and discover the secrets of our existence in the series. All matter in the universe can be found on the periodic table, a triumph of human understanding. Arranged by properties and atomic structure, the periodic table lets us read the fundamental story of the universe. Each box represents an element, each with its own unique combination of protons, neutrons, and electrons. But not all elements are created equal. We tend to focus on the most abundant or important ones. Gold, for instance, is both rare and precious. Meanwhile, iron is ubiquitous in Earth's crust, but hardly seems remarkable. By focusing on particular elements, we get a particular story of the universe. But to understand how the universe came to be, we need to step back and appreciate the whole periodic table, beginning with the very first elements. Up to now, we've explored the first second of the universe as though it were an abstract event, an immense explosion of physics, particles, and forces. But this moment is not just an academic curiosity. Without it, Earth would never exist. The very atoms in our bodies, the water in our oceans, the metals in our technologies, all can be traced back to the consequences of that first second. This segment shifts our focus from the grand universal stage to our home world. How did the violent beginnings of the cosmos, set in motion during that first second, eventually give rise to Earth, life, and civilization? The first elements determined the balance of protons and neutrons, and that balance dictated the chemical makeup of the universe. When nucleosynthesis occurred minutes later, it produced hydrogen, helium, and trace lithium, the primordial mix. Hydrogen became the dominant element, making up 3/4 of all matter. This was crucial, because hydrogen is the fuel of stars. Without it, stars could not have ignited nuclear fusion, and the universe would remain a dark soup of particles forever. Helium, the second most abundant element, would later serve as both a byproduct and stabilizer in stellar fusion cycles. Lithium, though rare, became a useful tracer for cosmologists to test Big Bang models. But notice what's missing. There was no carbon, no oxygen, no nitrogen. The elements essential to planets and life did not exist in the first minutes. They would be forged later inside the hearts of stars, whose formation was only possible because the first second set the ratios of hydrogen and helium correctly. Had those ratios been even slightly different, Earth might never have formed. Too much helium, and the universe's chemistry would stall. Too much hydrogen, and stars might collapse differently, never synthesizing the heavier elements needed for planets. In other words, the fine details of the first second are written into the periodic tableland into every rock, river, and organism on Earth. As stars formed and died, they scattered heavier elements across the galaxy. Supernova enriched the interstellar medium with carbon, oxygen, silicon, iron, and countless other elements. These materials recycled through generations of stars until, eventually, they condensed into molecular clouds, the birthplaces of solar systems. Our sun formed about 4.6 billion years ago from such a cloud. Embedded within it were the ashes of earlier stars, themselves descended from that primordial plasma born in the first second. The solar nebula collapsed under gravity, igniting the sun at its center and leaving behind a protoplanetary disk. From that disk, Earth assembled layer upon layer of rock and metal accumulating, shaped by collisions, gravity, and chemistry. The iron core, the silicate mantle, the oceans, and even the atmosphere can all trace their elemental origins back to that initial Big Bang nucleosynthesis and the star factories that followed. Every planet in our solar system, every asteroid and comet, is part of this story. The Earth is a direct descendant of the physics set into motion during the first second. Life on Earth depends on a handful of key elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Except for hydrogen, none of these existed in the first second. Yet hydrogen, the simplest atom, born directly from the Big Bang became the foundation. Hydrogen bonded with oxygen to form water, Earth's life medium. It powered the fusion engines of stars, which then produced the heavier elements necessary for DNA, proteins, and cell membranes. Hydrogen atoms in your body are literally 13.8 billion years old. They've never been destroyed, only rearranged, cycling through stars, clouds, planets, and eventually into living cells. This continuity is staggering. The glass of water you drink today contains hydrogen that was forged in the first 3 minutes after the Big Bang. Every breath you take binds you chemically to the first second of cosmic history. The sun, too, relies on the legacy of the first second. The sun's ability to shine for billions of years relies on the balance between gravity and nuclear fusion. That balance depends on the relative abundances of hydrogen and helium, and on the physical constants defined in the universe, S. First, second, the strength of the strong nuclear force, which holds atomic nuclei together. The strength of electromagnetism, which governs the repulsion between protons. The balance between matter and antimatter, which left just enough particles to form stars. If any of these constants had been even slightly different, the sun might never have formed, or if it did, it might not sustain stable fusion long enough for life to evolve on Earth. Thus, its very existence and its ability to harbor life depends on physics locked into place in that unimaginably brief first moment. Earth is not unique in this regard. All planetary systems rely on the same fundamental physics. And so the conditions set in place in the first second are a prerequisite for worlds beyond our own. But given the sheer number of planetary systems out there, you might think that Earth-like worlds should be common. So why are we alone? One possibility is that the conditions set in place during the first second of the universe are exceptionally rare. Perhaps the particular balance of matter, antimatter, subatomic particles, and physical forces is so finely tuned that our solar system is a statistical fluke. Or maybe it isn't. Maybe Earth-like planets are common, but something unique about our solar system sparked life here, while elsewhere it remains dormant. Either way, the question of why we are where we are remains one of the deepest mysteries of science. Our cosmic story began 13.8 billion years ago with a hot, dense singularity. Then came the Big Bang, a universe reshaping inflation, and a period of nucleosynthesis. These events, driven by the laws of physics, gave rise to the first atoms and set the chemical building blocks of the cosmos in motion. Hydrogen and helium dominated, but crucially, the conditions were set for the creation of heavier elements in the cores of future stars. Over eons, these stars synthesized heavier and heavier elements, enriching the universe with carbon, oxygen, silicon, iron, and more. Eventually, these materials coalesced into new stars and planets, forming the molecular clouds and protoplanetary disks that birthed our Sun and Earth. The exact proportions of elements resulted from a delicate balance of physical constants during the Big Bang, and that balance proved ideal for sustaining life as we know it. Certain elements like carbon, oxygen, and nitrogen became the fundamental ingredients of living things. And within our solar system, Earth became the Goldilocks planet capable of supporting life, because the physics of the first second set the stage for this possibility. But the story doesn't end here. Our sun's ability to shine for billions of years depends on this initial balance. And so far, it has provided the energy necessary for life to flourish. However, the question of why we are where we are remains. Is our situation truly unique, or are there countless worlds like ours out there? The answer could lie in unraveling the mysteries of the first moments of the universe, exploring the very foundations of our existence. If you enjoyed this video, make sure to watch the next one. In it, we'll explore the profound connection between humanity and the cosmos, emphasizing the vastness of space and time and our place within it. By understanding our origins and place in the universe, we gain a deeper appreciation for our existence and the challenges and opportunities that lie ahead. So join us in this thought-provoking journey and continue to expand your knowledge of the incredible universe we inhabit. It's easy to think of the first second as remote, a distant event happening in the cold void of space. But look again. Everything around you is a product of that moment. Every cell in your body, every mountain on Earth, every breath of air. All of it traces its origins back to the instant the universe came into being. Let's start with our planet. The story doesn't end with Earth's formation. Sure, that was a big moment. But many of the ingredients that made this planet habitable also arrived after it was born. Take water, arguably the most critical ingredient for life as we know it. Comets and asteroids, icy bodies orbiting the sun, delivered water molecules to Earth over billions of years. Many scientists think this delivery was crucial for the development of life. But where did those water-rich bodies come from? To answer that question, we have to look back to the first second. See, comets and asteroids are largely composed of hydrogen and oxygen. Those two elements combined make water. And the only way they could have formed in the first place was through the nuclear processes that began in the first second. Now here's where things get complicated. There are different kinds of hydrogen and different kinds of oxygen. Each has a different number of protons. During the first second, only the simplest forms of these elements could have formed. Don't worry, this won't be a pop quiz. The point is that the hydrogen and oxygen found in comets and asteroids and thus on Earth are chemically identical to the stuff that existed in the first second. They are literally Big Bang leftovers. These icy bodies didn't just deliver water. They brought other ingredients for biochemistry too. Asteroids in particular are rich in organic molecules, complex compounds based on carbon. Some asteroids contain amino acids, the building blocks of proteins. Others have nucleobases, the components of DNA and RNA. Together, these organic molecules make up the essential machinery of life. But again, they are only possible because of the primordial hydrogen and oxygen forged in the first second. That means the story of Earth doesn't begin with Earth. It begins long before, with a moment of unimaginable heat and energy. Indeed, the conditions that prevailed in the universe's first second determined what elements could exist, which atoms could combine, and in what quantities. It set the stage for everything that happened next, including the birth of stars. Stars are the cosmic engines that forge the heavy elements that make up planets and people. Our sun, for instance, is mostly hydrogen and helium, the simplest elements which formed in the first second. But stars more massive than the sun are capable of producing elements much heavier than helium. This is possible thanks to the extreme temperatures and pressures found in the cores of these stars. Their hydrogen is converted into helium, and amazingly, all the way up the periodic table, including iron. Iron is the endpoint of stellar nucleosynthesis. No star can produce elements heavier than iron, because they require more energy to make than the star can provide. What happens to those iron-making stars? They explode as supernovas, leaving behind neutron stars or black holes. These collapsed stellar corpses can kickstart new stars by triggering the collapse of nearby gas clouds. And those new stars will be capable of forging still heavier elements, including the stuff that makes terrestrial planets like Earth solid. That means the conditions in the universe's first second indirectly led to the formation of entire planetary systems, including our own. But let's think even bigger. The conditions in the first second also had implications for the chemical activity happening on Earth's surface. For example, mass extinctions, like the one that ended the reign of the dinosaurs 66 million years ago, can be seen as a result of the conditions established in the first second. Without the asteroid that delivered the final blow, mammals might never have risen to prominence, and humans might not exist. And ironically, that asteroid was itself a fragment of primordial material, a chunk of rock torn from the sun during the formation of the solar system and flung into the outer reaches of the planet. In a very real sense, even Earth's catastrophes are rooted in that first second. So the first second wasn't just a moment when the universe began. It was a moment when the potential for Earth began. From the chemical activity of our planet's core to the composition of our atmosphere, from the rise of organic molecules to the extinction of the dinosaurs, everything that has happened on Earth since then can be traced back to that instant. The human connection, it's easy to think of the first second as remote, a distant event happening in the cold void of space. But look again. Everything around you is a product of that moment. Every cell in your body, every mountain on Earth, every breath of air, all of it traces its origins back to the instant the universe came into being. When Carl Sagan said, "We are made of star stuff," he was telling only part of the story. We are made not only of star stuff, but of Big Bang stuff. Hydrogen, the most abundant element in your body, is as ancient as time itself. It is a relic of the universe's very beginning. The Earth is not an isolated world. It is a crystallization of cosmic history, shaped by forces and laws that began in the universe's first second. A planet written by the first second, the takeaway is profound. If we want to understand Earth, not just its geology and biology, but its very possibility, we must understand the first second of the universe. That fleeting moment was the blueprint. It determined which elements could exist, which stars could shine, and which planets could form. From the Big Bang to the Big Blue Marble, there is an unbroken chain of cause and effect. And at the heart of that chain lies the most mysterious second in history. This is our digital channel. The first seconds of the universe are a time of great drama and change. Forces invisible to the human eye wove together the very essence of reality, establishing the framework of space, time, and matter. Within this fleeting instant, the seeds of galaxies, stars, and planets were sown, and in the stage for the grand cosmic ballet that has continued for billions of years. Yet despite their monumental significance, understanding the events of the first second has eluded us for centuries. It's a testament to the complexity of the universe that even today, scientists are still working to unravel the mysteries of this primordial time frame. In this episode, we want to share our own exploration into the heart of these enigmatic moments. Through the latest research and data analysis, we were going to try to visualize and understand what happened in the first second of the universe's existence. We'll examine the groundbreaking work of scientists who have come tantalizingly close to unlocking the secrets of this era, revealing the incredible challenges they face and the awe-inspiring discoveries they've made along the way. Join us as we embark on a thrilling journey through the uncharted territories of the cosmos, seeking to comprehend the extraordinary events that unfolded in the first moments of time. For much of human history, the idea of a universe that began with a bang was nothing more than a fantastical notion. Many cultures wove tales of creation involving gods or mystical forces bringing the world into being. However, the concept of a beginningless cosmos was widely held until the scientific revolution of the 16th and 17th centuries. Pioneers like Copernicus, Galileo, and Newton challenged long-held beliefs about the Earth's place in the universe and the laws governing celestial bodies. This shift in thinking paved the way for the idea that the universe itself had a beginning. With the invention of the telescope, we began observing the heavens in a whole new way. Galileo's discovery of moons around Jupiter and other celestial wonders shattered the notion of an immutable cosmos. The realization that the universe was dynamic and ever-changing opened the door to the possibility of a beginning. And so the idea of a primeval explosion gradually emerged, taking root among astronomers and scientists. But it was not until the 20th century that we started getting closer to pinpointing what really happened in those crucial first seconds. Albert Einstein's theories of special and general relativity laid the foundation for our current understanding of the universe. His description of gravity as the curvature of space-time caused by mass and energy allowed scientists to envision the universe as a dynamic entity governed by natural laws. When the Russian mathematician Alexander Friedmann discovered that Einstein's equations allowed for the concept of an expanding universe, it provided a missing piece of the puzzle. If the universe was expanding, it implied that all celestial objects were moving away from each other, a phenomenon confirmed by Edwin Hubble's observations in 1929. This revelation led to the theory of the Big Bang, which posits that the universe originated from an extremely hot, dense state and has been expanding ever since. A key prediction of the Big Bang theory is the existence of a faint glow of light left over from the early stages of the universe, known as the cosmic microwave background radiation. Though it took several decades to detect, the discovery of the CMB in 1964 by Arno Penzias and Robert Wilson provided strong evidence supporting the Big Bang model. This relic of the early universe offers an invaluable window into the conditions. Just 380,000 years after the Big Bang, when the universe was still incredibly hot and luminous. By studying the CMB, scientists can probe the fundamental nature of the cosmos during this primordial period and gain insights into the processes that shaped the universe as we know it today. However, the path to comprehending the complexities of the universe's infancy has been fraught with challenges. Scientists have had to overcome significant hurdles in their quest to unlock the secrets of the early cosmos. One major obstacle has been the sheer scale and immensity of the universe. In the first second alone, the universe expanded by a factor of 10 trillion, a mind-boggling rate of growth that makes it difficult to comprehend the distances involved. Another challenge has been the limitations of current technology and scientific instruments. Despite remarkable advances in observational capabilities, our tools are still insufficient to fully map and analyze the intricate details of the universe's early moments. Furthermore, the lack of direct observational evidence for many aspects of the early universe presents a significant barrier to understanding. Scientists must rely on indirect methods and theoretical models to piece together the sequence of events that occurred in the first second. This inevitably introduces uncertainties and gaps in our knowledge, leaving many questions unanswered. Perhaps most daunting of all is the complexity of the underlying physics. The conditions in the early universe were so extreme and unfamiliar that they defy our current understanding of natural laws. Probing into this uncharted territory requires pushing the boundaries of physics, questioning established theories, and developing new frameworks to explain the phenomena we observe. Despite these obstacles, scientists have made remarkable progress in unraveling the mysteries of the first second of the universe. Through meticulous observations, theoretical modeling, and innovative experimentation, they have pieced together a coherent picture of this pivotal moment in cosmic history. As technology continues to advance and our understanding deepens, we can expect to make even greater strides in comprehending the awe-inspiring events that unfolded in the blink of an eye some 13.8 billion years ago. In the late 1980s, researchers theorized that the initial moments of the universe went through a period of exponential expansion known as inflation. This idea offered an explanation for certain features of the cosmic microwave background radiation, such as the uniformity of its temperature and the distribution of matter in the universe. However, direct evidence for inflation remained elusive, leaving scientists grappling with its plausibility. Enter the BICEP collaboration. A team of astronomers led by researchers at Harvard University and the Massachusetts Institute of Technology. In 2014, they claimed to have found evidence of inflation in data from the BICEP telescope in Chile, which studies the polarization patterns in the CMB. The team argued that their observations supported the inflationary model, suggesting that the universe underwent a brief period of rapid expansion in the first fraction of a second after the Big Bang. However, Their findings were met with skepticism, as some scientists questioned whether the BICEP team had correctly identified the signal. They attributed to inflation. Critics pointed out the possibility that the signal might have resulted from dust in our galaxy rather than from inflation. Undeterred, the BICEP team, along with other collaborations like the Planck experiment, continued to analyze data and refine their measurements. By combining their results, scientists aimed to provide a more conclusive assessment of the inflationary model. However, as more data became available, the evidence for inflation weakened. In 2018, the Planck collaboration announced that their analysis of the CMB did not support the claims made by the BICEP team. The discrepancy between the two sets of results highlighted the challenges of making definitive statements about the early universe based on indirect observations. Nevertheless, the quest to confirm or refute inflation remains a driving force in cosmology, prompting scientists to push the boundaries of detection and analysis in their quest to unlock the secrets of the universe's birth. As we continue to explore the mysteries of the first second, we re-confronted with the immense challenge of reconciling the predictions of our theories with the complexities of the real world. One such challenge lies in explaining the abundance of elements in the universe, particularly the relative amounts of hydrogen, helium, and heavier elements. The Standard Model of Big Bang Nucleosynthesis, or BBN, attempts to explain the observed abundances of these elements based on the conditions prevailing in the early universe. However, it faces discrepancies when it comes to predicting the amount of helium. Scientists have noted that the amount of helium observed in the universe is higher than what can be accounted for by the Standard Model. This anomaly has sparked debate and speculation about possible solutions. Some researchers have suggested modifications to the Standard Model, such as the existence of alternative sources of helium production in the early universe. Others have proposed adjustments to the model's parameters to better align with observations. However, these adjustments often introduce new problems or require fine-tuning that doesn't sit comfortably with the scientific community's desire for simplicity and elegance in theories. To resolve this puzzle, scientists are pursuing various avenues of inquiry. One promising approach involves studying the properties of neutron stars, which are the ultra-dense remnants of massive stars that have exploded as supernovas. By analyzing the behavior of neutron stars, researchers hope to gain insights into the nuclear reactions that occur during the synthesis of elements in the early universe. Additionally, experiments aimed at recreating conditions similar to those in the early universe on Earth are underway. By precisely controlling temperatures and particle concentrations, scientists can observe the formation of light elements under conditions that mimic the moments immediately following the Big Bang. As these investigations continue, we may find that the universe's elemental makeup holds clues to the events that transpired in the first second, shedding light on the processes that shape the cosmos as we know it today. By delving into the intricacies of nucleosynthesis, scientists are uncovering the building blocks of the universe and shedding light on the remarkable journey that led to the creation of elements in the first second. While we may never know every detail of what happened in the first second of the universe, we have come a long way in our understanding. Thanks to the tireless work of countless scientists and researchers, we now have a much clearer picture of the amazing events that unfolded in those crucial moments after the Big Bang. If you enjoyed this video, please don't forget to like and subscribe. Your support means everything to us. We can't wait to bring you more exciting space discoveries in the future. Until then, keep looking up and keep asking questions. Who knows what wonders we might uncover next? The first second. Our earliest ancestors were making rock tools. The Milky Way was a baby, a mere 100 million years old. In the universe, well, it was barely 1 trillion seconds into its existence. Today we know that in that first second, the universe went from a hot, dense soup to a cosmos filled with galaxies, stars, and yes, us. But we didn't learn this by staring up at the night sky, at least not directly. Instead, we used a different kind of telescope. One that allows us to peer into the past by recreating the conditions of the first second here on Earth. Here's how we see the first second backwards. Photons from the cosmic microwave background, or CMB. The remnant radiation from the Big Bang reach Earth after traveling 13.8 billion years. Each photon carries a tiny bit of information about the universe at the moment it left the cosmic microwave background. 380,000 years after the Big Bang. But the information is faint and hard to decipher. To understand what happened in the first moments of the universe, we need more data. We need to conduct experiments. And that brings us to particle accelerators, machines like Fermilab's, Tevatron, and CERN's Large Hadron Collider, the LHC. These accelerators smash particles together at nearly the speed of light, reproducing, for a fleeting instant, the energies of the first trillionths of a second. After the Big Bang, the universe cooled rapidly, allowing subatomic particles called quarks to come together and form larger particles called mesons and baryons, the building blocks of matter. Physicists think these particles interacted via the exchange of other particles called vector mesons. Studying vector mesons could tell us how matter came together in the early universe. But those particles are unstable and decay in a timescale of a few trillionths of a second. That means the only way to observe them is to recreate the conditions under which they formed, smashing particles together and then measure what comes out. In 2012, the LHC confirmed the existence of a particle predicted by the Standard Model of Physics, the Higgs boson, the Higgs field. Active in the first second is what gives particles their mass. Without it, atoms and, by extension, planets and people would not exist. Accelerators also allow physicists to test theories of quark-gluon plasma, symmetry breaking, and matter-antimatter interactions, all processes rooted in that mysterious first second. But while particle accelerators help us understand what happened after the Big Bang, they can't tell us what caused the rapid expansion known as inflation. Nor can they shed light on the details of the universe's formation in the first few minutes. For that, we need to look to the sky. There, the faint glow of the cosmic microwave background holds clues about the universe's evolution. Experiments like the BICEP collaboration attempt to measure temperature variations in the CMB, searching for imprints of inflation. Meanwhile, experiments like LIGHTBIRD will measure the polarization of the CMB, which can reveal details about the universe's shape and how matter came to be distributed throughout the cosmos. Each new experiment adds another piece to the puzzle of the first second, each measurement bringing us closer to a deeper understanding of the universe's origins. Our observations of the CMB and our experiments in particle accelerators are not just separate endeavors. They complement and reinforce each other. Each type of evidence supports and deepens the other. Together, they paint a coherent picture of the universe's infancy. What's remarkable is not only what we've discovered, but how we discovered it. With fragile machines built by human hands on a small planet in one galaxy, we've managed to reconstruct the first second of the universe. Think of the scale involved. The photons of the CMB we detect today have traveled for 13.8 billion years to reach us. The particles we study in accelerators exist for trillionths of a second before vanishing. Yet from this evidence, humans have built a coherent picture of the universe's beginning. This is a triumph of the scientific method: observation, theory, experiment, revision. It is also a testament to our curiosity. From myths told around fires to satellites orbiting Earth, humans have always asked the same question: where did it all begin? Our journey from myth to measurement shows something profound. Though the universe is vast and ancient, it is not beyond our comprehension. By building tools, asking questions, and looking outward, we've managed to reach back across billions of years and touch the very first second of time. The first second created the blueprint of the cosmos. Humanity, through science, has learned to read that blueprint. Now we're going to take that a step further. Join us as we continue to explore the first, second, and all of the incredible discoveries that are sure to come our way. Now we have followed the story of the universe's first second, from the birth of space-time itself. Through cosmic inflation, the formation of matter, the emergence of light, and humanity's gaze into the cosmos. But the journey does not end here. In fact, the more we learn about the first, second, the more profound and unsettling our questions become. What does it mean that everything, the galaxies, the stars, Earth, and ourselves, was encoded in the physics of that single moment? What lies beyond the Big Bang? And how might answers to these questions shape the future of science, philosophy, and even civilization? This final segment explores the future implications and unanswered mysteries that flow from studying the first second, the quest for the beginning of the beginning. The Big Bang Theory describes how the universe evolved after it began, but it does not explain why it began. It tells us nothing about what came before, if such a concept even makes sense. Physicists are now probing deeper into this frontier. Some hypotheses suggest that the Big Bang was not the absolute beginning, but a transition. Quantum cosmology proposes that space-time itself emerged from quantum fluctuations. In this view, the universe could have tunneled into existence from nothing. The bounce hypothesis suggests that our Big Bang may have been preceded by a big crunch, a collapsing universe reborn in a cycle of expansions and contractions. String theory envisions higher dimensions, where our universe might have been born from the collision of cosmic brains floating in a larger multidimensional reality. Each idea pushes us further back in time, before the first second we understand. But for now, none of these scenarios can be proven. What we know for certain is that our familiar physics breaks down at the singularity. The laws we rely on, general relativity, quantum mechanics, cease to function when compressed to that extreme. So the search for the true origin of the universe remains open. Inflation. Clues written in the sky. Inflation. The theory of ultra-rapid expansion in the universe's first instant elegantly explains many features of the cosmos. But was it real, or just a useful mathematical trick? The key may lie in gravitational waves. Inflation would have produced faint ripples in space-time, primordial gravitational waves that could still echo today in the cosmic microwave background. Detecting these signals would be one of the greatest scientific achievements in history, offering direct evidence of inflation and perhaps even insights into physics at energies far beyond what particle accelerators can reach. Projects like the BICEP array in Antarctica and future space missions are designed to hunt for these primordial signals. A detection would not only confirm inflation, but also open a window into physics at scales close to the Planck era, less than 10 seconds after the Big Bang. The multiverse. Are we alone in reality? Perhaps the boldest implication of inflation is the idea of the multiverse. According to some versions of inflationary theory, our universe may not be unique. Inflation might produce countless pocket universes, each with its own laws of physics, its own constants, even its own dimensions of time and space. In such a scenario, the properties of our universe, the strengths of forces, the values of constants, the balance of matter and antimatter, could be accidents of cosmic lottery. We live here not because it is inevitable, but because only in universes like this one can life arise to ask questions. This raises profound questions. If countless universes exist, can we ever detect them? Does the multiverse explain why our universe appears fine-tuned for life? Or is the idea forever beyond the reach of science? A philosophical reflection disguised as physics. While direct evidence remains elusive, the multiverse is no longer fringe speculation. It emerges naturally from serious mathematical models. Whether it is true or not, its consideration reveals how studying the first second leads us to the edge of what science can currently explain. The fissures in our understanding. There are signs that our understanding of the first second, while detailed, is fundamentally incomplete. The horizon problem. One of the greatest triumphs of the Big Bang model is explaining the universe's large-scale structure, yet it poses an enigma. The universe is remarkably homogeneous and isotropic, meaning it looks roughly the same in all directions. But regions of the universe that are so far apart, light has not had time to travel between them since the Big Bang should not be so similar. They are, according to the Big Bang, causally disconnected. How did they manage to coordinate to be so alike? Inflation solves this puzzle by stretching space in the early universe. Regions that are now distant were once neighbors. Inflation makes the universe inhomogeneous at small scales. But those tiny variations grow into the large-scale structure we see today under the influence of gravity. This elegantly resolves the horizon problem. However, it leaves another mystery. Why do the variations in the cosmic microwave background radiation appear so smooth? Shouldn't there be more lumps in the distribution of matter at the time? Quantum fluctuations during inflation could help explain this conundrum. The flatness problem. The Big Bang model also successfully describes the geometry of space. Our universe is remarkably flat. On the largest scales, the overall effect of gravity should have caused space to curve. But observations of distant supernovae show that the universe remains astonishingly flat. The simplest explanation is that the universe started off with a very specific and finely tuned curvature. But why would this be the case? Here too, inflation comes to the rescue. The theory of eternal inflation suggests that our universe is just one bubble in a vast foam of inflating space. We reside within a particular region that has deflated from this rapid expansion, giving the illusion that we live in a flat universe. However, this raises another question. Why did our bubble deflate at just the right time to produce a universe suitable for life? Is this, too, just a cosmic lottery? Or are there other forces at play? The future of fundamental physics. As we probe deeper into the mysteries of the first second, we face formidable challenges. Limitations in current technology hinder our ability to test theories about the earliest moments of the universe. This fuels a race for new and innovative approaches. For instance, efforts are underway to develop new telescopes to observe the cosmic microwave background in greater detail, searching for imprints of inflation and the seeds of the large-scale structure. Meanwhile, theoretical physicists are pushing the boundaries of mathematics, developing new models to describe the universe at extreme energies and scales. They are exploring concepts like quantum cosmology and string theory to unravel the nature of space-time at its most fundamental level. However, even with these advancements, there will be limits. The further we push, the more we encounter phenomena that lie beyond the reach of current or foreseeable technology. This raises fundamental questions about the nature of knowledge and the limits of human understanding. Can we ever hope to comprehend the origins of the universe? Or are there some mysteries that lie beyond our grasp? Moreover, the implications of discoveries about the first second extend far beyond the realm of science. They touch upon deep philosophical questions about our place in the cosmos. If the universe is fine-tuned for life, does that imply a purpose or design? And if we find evidence of a multiverse, how should we think about the nature of reality? These discoveries will undoubtedly challenge our existing beliefs and force us to confront profound questions about the meaning of existence. Navigating ethical frontiers, the quest to understand the first second also raises ethical challenges. As we probe deeper into the mysteries of the universe, we may encounter phenomena that challenge our intuitions about reality. For example, if we discover evidence of eternal inflation, it could imply that there are other universes where different physical laws hold. This might lead to questions about the validity of our own physical laws and the nature of scientific knowledge. Moreover, as we push the boundaries of technology to observe the early universe, we may face ethical dilemmas. For instance, the use of large-scale computing for simulations of the early universe could raise concerns about data privacy and the potential for misuse. As we delve deeper into the mysteries of the first second, it is crucial to engage in thoughtful and inclusive discussions about the ethical implications of our discoveries, shaping the future. In conclusion, the study of the first second promises to shape the future of science, philosophy, and our understanding of the universe. As we continue to probe the mysteries of the cosmos, we can expect exciting discoveries that will revolutionize our knowledge. However, these discoveries will also challenge our intuition and raise profound questions about the nature of reality and our place in the cosmos. To navigate these challenges, it is essential that we foster interdisciplinary collaboration between scientists, philosophers, and ethicists. By working together, we can ensure that our exploration of the early universe is not only intellectually stimulating, but also ethically responsible and beneficial to humanity as a whole. The quest to understand the first second is a testament to the boundless curiosity and spirit of exploration that drives humanity forward. As we continue to unlock the secrets of the cosmos, we can be inspired by the profound beauty and complexity of the universe we inhabit. Let us embrace the challenges and opportunities that lie ahead and strive to deepen our understanding of the wonders that surround us. The support of our viewers is vital to our mission. Your support allows us to continue exploring the mysteries of the universe and sharing our findings with the world. Together we can unravel the deepest secrets of the cosmos and inspire future generations of scientists and dreamers. If I told you the heat death of the universe happens right here, you'd probably think I'm making some dramatic point. Here, look. It's a chart with a number of different possible scenarios for the heat death of the universe, also known as heat death. Now you might be wondering why. I'm telling you the heat death of the universe happens at home because it does. The heat death of the universe happens out there in space. But here's the thing. The way the universe ends depends on what's happening right now. So if you want to know what happens when the universe reaches maximum entropy, cold, and dark, well, You have to start looking at what's happening in the very first second after the Big Bang. So let's take a journey back to the beginning. Welcome to Minute Earth. In the first second after the Big Bang, the universe went through a lot of changes. It expanded by a factor of 1 million. Quarks came together to make protons and neutrons. Those combined to make atomic nuclei. And electrons were whizzing around those nuclei. That makes the first second sound pretty similar to the universe as we know it today, except that wasn't true. It was actually a hot, dense plasma. The universe was so hot that the particles we associate with normal matter couldn't stay in their lowest energy state. Everything was super excited. This period is called matter domination because matter had not yet turned into anything else. But soon it would. After only a second, the universe was still expanding. But the expansion wasn't accelerating, so that rules out this heat death scenario where dark energy takes over and causes the expansion to accelerate. Also, the average matter in the universe wasn't moving fast enough to rip apart hydrogen or any other kind of atom. So that means that the big rip, where everything gets torn apart by the accelerated expansion of the universe, also can't be what happens to our universe. Instead, at this point, the universe was cooling off fast. The stuff in it was slowing down, and as it slowed down, it started to clump together under the influence of gravity. This is sometimes called the era of structure formation, and that clumping together is happening today. Gravity is pulling together the stuff in the universe, forming new stars and galaxies, and growing larger and larger. That means that the big crunch, where the expansion of the universe flips, and our universe literally begins to collapse, also isn't going to happen. Right now, the amount of dark energy in the universe seems to be the same everywhere we look. It's constant. But that doesn't have to be the case. Dark energy could change over time. And if it did change, it could change in such a way that it pulls things together instead of pushing them apart. But we don't know if that's physically possible, let alone likely. So for now, we have to put that option aside now. We don't have direct evidence for any of this. All we have is the cosmic microwave background, a faint glow of radiation left over from the Big Bang. This radiation stretches as the universe expands. The photons themselves don't move faster than the speed of light. They just get stretched out so the wavelengths get longer. This means the cosmic microwave background has gotten cooler as the universe has expanded. Today, the cosmic microwave background is only about 2.7 Kelvin, but when it was just a second old, it was around 4,000 kelvins. That's over 3,700 degrees Celsius. And that tells us that the stuff in the universe was moving really fast. Photons were bouncing off of particles constantly. So if you wanted to measure the temperature, you'd have to measure the average kinetic energy of all the particles. But the fact that the cosmic microwave background was so hot tells us something else. That there wasn't a whole lot of stuff in the universe yet. That is because while we can use the cosmic microwave background to measure the average kinetic energy of particles in the universe, we can also use it to measure the total amount of matter in the universe. If there were more stuff in the universe, there'd be more stuff for the photons to bounce off of. And we see fewer of those interactions in the cosmic microwave background. So the simple explanation is that 1 second after the Big Bang, there wasn't much stuff in the universe. There was barely any ordinary matter at all. Most of the matter we see today formed over billions of years after the Big Bang. The only exception is helium, which began to form a few minutes after the Big Bang. But that wasn't the only thing that was around in the first second. Even though there wasn't much matter around, there was plenty of radiation, a sea of photons, neutrinos, and other particles streaming around. And that matters because the amount of radiation in the universe today depends on the amount of radiation that was around in the first second. That's because photons, like all massless particles, travel at the speed of light. So they haven't had time to get anywhere else since the first second. And neutrinos, like all massive particles, travel slower than the speed of light, so they didn't get far away either. So the ratio of photons to matter in the universe today is pretty much the same as it was in the first second. And knowing that ratio is important because if there was more radiation than we expect, it would mean some of the radiation from the first second has converted into matter since the first second. And if that happened, it would mean that there are new forces of nature at play that we don't know about. We're looking for that right now. We're also looking for other signs of new physics from the first second. Like, for example, a lot of particle physicists think that, in the first second, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were actually one single force. So they re-looking for signals of that unified force in particle collisions at places like the Large Hadron Collider. If they find evidence of that, it would mean that our theories of the first second are wrong. And while that might not sound like a good thing, remember that every scientific theory is just an approximation of reality. A better theory just means a more accurate description of reality. For example, Newton's equations describe the motion of objects really well under most circumstances. But Einstein showed us that those equations break down at very high speeds and near very heavy objects. That doesn't mean Newton was wrong. This means that his theory was a useful approximation for describing most of the things we encounter in everyday life. It's just not 100% accurate, and that's okay. Approximations are the basis of all scientific progress. In the same way, our best current theories of the first second are approximations. And if they're wrong, it'll open up new avenues of research, new ways of understanding. And if they're right, then we'll have confirmed our current understanding of the first second, which means we'll have confirmed our understanding of how the universe got started. And that's why it matters, because the physics of the first second still governs the physics of today. The balance of matter, radiation, and dark energy that was established long ago still determines the trajectory of everything today. So the more we learn about the first second, the more we learn about the universe now and in the future. Take, for example, the cosmic microwave background. It's not just a record of the first second. It's also the fabric on which galaxies form. That's because the tiny temperature variations in the cosmic microwave background correspond to tiny variations in the distribution of matter in the universe. Those variations are like seeds from which the large-scale structure of the universe grows. And as galaxies grow, their shape and evolution also depend on the details of the cosmic microwave background. And the same thing happens on smaller scales too. Atomic nuclei and molecules form and evolve according to the laws established in the first second. Chemistry and biology depend on the properties of atoms. Our ability to detect and manipulate those atoms depends on our understanding of the first second. That's say, studying the first second has technological implications that go beyond the immediate goals of fundamental research. The tools developed to study the early universe cryogenics, superconducting detectors, massive data analysis techniques have applications across medicine, engineering, and computing. The algorithms used to map the cosmic microwave background also help process medical imaging. Developments in particle physics drive advances in energy, materials science, and artificial intelligence. Studying the first second also has deeper implications. It reminds us that we are the outcome of a chain of physical events stretching back nearly 14 billion years. Every atom in our bodies was shaped by laws established in that primordial instant. Understanding that doesn't just satisfy curiosity. It also shapes how we see ourselves, our place in the universe, and the fragility of the conditions that allow life to exist. As we stand on the edge of understanding, several ultimate questions remain. Why is there something rather than nothing? Are the laws of physics universal, or are they local to our cosmic region? Can science ever penetrate the true beginning, or is there a fundamental horizon to knowledge? If the universe is one of many, what does that mean for meaning, for purpose, for existence itself? These are not only scientific questions, they are philosophical, even existential. But they emerge naturally from the study of the first second. The first second of the universe is both the most fleeting and the most consequential moment in history. It established the architecture of reality, the framework upon which everything else unfolded. From a fraction of a second of expansion, a cosmos of 2 trillion galaxies was born. From the symmetry breaking of fundamental forces, the richness of chemistry and biology emerged. From the faint afterglow of the Big Bang, human beings, billions of years later, learned to read the story of creation itself. In studying the first second, we are not only looking backward in time, we are looking into the foundation of everything. Thanks for watching this episode, which was brought to you with the help of our patrons. Just like the universe, our channel was born in a hot, dense state and has evolved over time. Our supporters help us continue to expand, allowing us to explore new topics and reach more viewers than we could ever do alone. You can join our incredible community of supporters at our support page